Hello, IB Math 2 students. Looking at some more to do with functions today. This is in the Orange Book, section 3C, especially focusing on domain and range. Let's see here. Yeah, there we go. So the domain, here's the definition of a relation, is the set of values which the variable on the horizontal axis can take. This variable is usually x. The range of a relation is the set of values which the variable on the vertical axis can take. This variable is usually y. Another thing to think about is, so if you're just looking at this curve right here. So here's the curve. All right. We're looking at this curve. Notice that it has a point right here and a point right here, not an arrow. If it had an arrow, then we would assume it goes up forever, right? But it doesn't have an arrow, it has a point, so then we assume that it stops at that point. So another thing to keep in mind is when we're looking at the domain on the x-axis, we always express the domain from the least number to the greatest number. So let's just say that this was the number 3, and this goes all the way to the number 9. Having to draw with my fingers, not looking too good, hoping you can see that. We wouldn't say that the domain goes from 9 to 3. We would say the domain goes from 3 to 9. That means x can take all the values from 3 to 9. You could express that with an inequality like this. X goes from 3 to 9, like that. Or you could express it with an interval, 3, 9. And notice I have put brackets on this. To say that those numbers are included. Why are they included? Because they have points that are closed in right there. That means they actually get to that point. They touch that point. So that would be the domain. Here, the range, again, you read it from least to greatest. So you would read it from bottom to top, not top to bottom. So let's just say that this was, I don't know, let's say that this one started at 4 and ended at 8, let's say. So we could express that as the range being the y values between 4 and 8, not between 8 and 4. So we always give it from least to greatest, which means from low to high on the y-axis. We could also do this one with an interval like so. Okay. All right, this says the domain and range of relation can be described using set notation, interval notation, or a number line graph. So if we were expressing the domain here, we could use set notation, and we remember what this means. This means all x such that x is greater than or equal to 3. Or just interval notation is kind of the same thing, just not using these brackets and this x with this vertical line. Interval notation is the same thing it says here, though, is here. And we could also draw this on a number line. You know, x is everything greater than 3. We could express that using this number line with this point and this line with an arrow, saying that x is everything to the right of 3. Set of all x such that x is greater than or equal to 3. All right, this one is x is less than 2. You can see that there's an open circle here and everything to the left of that. Here, x, the set of all x in it, and I should remind you that this means x is all of the real numbers. So when it doesn't say all of the integers or all the natural numbers or something, then it means if it doesn't have anything at all, it's understood to be x is all the real numbers. So all real numbers x, such that x is between -2 and 1, not including the -2, but yes, including the 1. All right, so notice how on the number line it's an open circle on the -2, a closed circle on the 1. Here we have 2 different intervals for x. So x is everything less than or equal to 0, or x is everything greater than 4. So you would express that over here with 2 different parts of the number line. So a point on 0 and an arrow going to the left, an open circle on 4 with an arrow going to the right. All right, so let's look at number 3 here. Looking at this parabola, what do you think is the domain? That means what all values on this x-axis are included in this curve, or have a point represented somewhere in this curve. Well, the arrows are on the curve means that it continues on forever in this direction. So if we read this thing from left to right, and it continues on forever to the left, what's the lowest value that is included in this curve? Well, it would be negative infinity. Since this thing goes forever to the left, you could say the domain starts at negative infinity. All right, and all of these numbers, all of these values on the x-axis, every infinitesimally small value on the x-axis has a point somewhere represented in this curve, right? This one has a point right here. All these values do. And notice the arrow continues going to the right forever, so where does the domain stop? Well, it goes all the way to positive infinity. So the domain would be, we could say, negative infinity to infinity. Parentheses on that, because you never reach infinity. A short way to say that is if it includes all the numbers from negative infinity to infinity, you can just say it's all the real numbers. So the domain is all real numbers. You can use a double bar R to represent that. That's, instead of saying negative infinity to infinity, it's the same thing as saying that. All right. What about the range here? The question would be, how low, what's the lowest value on this y-axis that is included in this curve? And since the curve continues going down forever, you could use either arm to surmise that. Since it goes down forever, the lowest value on the y-axis that is included in this curve is negative infinity. All right, but then you say, well, what's the highest value, included in this curve? Well, we can certainly say that 4 is not included in the curve. So since this point is the highest that it gets, and it's the point 2, 1, what is the highest y value that this curve hits? It would be 1. All right, so I know I didn't draw my dashes right to say that. Let me see if I can. Let me see if I can erase. I don't think I can. Let me see. I was able to erase. I had to pause it to figure out how to erase it, but let me draw my dashes a little better to fit what it's saying that point is. So the highest this curve gets is 1 on the y-axis. So then it goes from negative infinity all the way up to 1. So we could say negative infinity to 1. We would not include the negative infinity, but we would include the 1. All right, another way to say that is, we could say y is from negative infinity to 1, including the 1. But you don't really need to say y is greater than negative infinity, because that's just kind of a understood thing already. Like y is obviously greater than negative infinity, so we can just leave that part out and just say y is less than or equal to 1. And that would say it's everything from here on down. So that's what they say right there. That's another way to say it. All right, look at number 4 and see if you can determine the domain and range of that problem. All right, if we start at the left, how far to the left does this function go? It continues forever. So it starts at negative infinity. Pardon my handwriting, it's hard to draw on this screen with my finger. And it continues to have values, like all these values on the y-axis. Every one of these infinitesimally small values on the y-axis is represented in that graph somewhere, right? Until you get to this vertical asymptote. At x equals 2, there is no point on the graph. So we would say it goes from negative infinity to 2, not including the 2. But then after the 2, like all these values, are included there. So I would say union 2, and it goes on forever to the right, so all the way to infinity. That's one way to say it. All right. Another way to say it is you could say x is all real numbers except for 2. And that's what is said right here. If you just say all x, which is understood to be all real numbers, x, such that x does not equal 2. So everything but 2. And that's probably, that's a good way to say it. It's a little bit shorter way than this is to say it. Or what about the range? Start at the bottom. What all values on this y-axis have points somewhere on that curve? Since it goes down forever, it starts at negative infinity. And all these values have a point somewhere on that curve until you get to what? Until you get to this horizontal asymptote, which is at y equals 1. So it goes from negative infinity to 1, but it doesn't include the 1. And then everything after the 1, all these infinitesimally small values are somewhere included as points on this curve, and it continues to go on forever up. So it would be from 1, not including the 1, to infinity. So that would be a good way to express your range. But look what they did. They did it a little bit easier way, a little shorter way. They said y is all real numbers y, such that y does not equal 1. So y is every real number, the range is every real number except for the one that y doesn't equal. So it's every real number except for 1. So that's a good way to express it also. All right, to fully describe a function, we would want both a rule, that's an equation usually, and a domain. So for example, here's the equation or the rule, f of x equals x squared. So that describes the function, but then we might limit the domain. We might say only where x is greater than or equal to 0. That may be the only thing we care about. All right, so doing that this fully describes a particular function that we are interested in at this moment. All right, if you don't specify the domain, then you would assume what's called a natural domain. That is the natural mathematical domain, which is the largest part of all real numbers for which f of x is defined. So for f of x equals x squared, what all numbers can you plug in for x and get a nice, normal, defined answer? If you put in negative a billion, you would square it and get a really big number. If you put in 0, you would square it and get 0. If you put in a million, you would square it and get another really big number. So all the numbers you could possibly think of, you could put in for x, and you could square it, and you would just get a regular, nice, real number. So the natural domain of that, which tells us right here, is x squared. The natural domain for that is all real numbers, because you can plug any real number in for x, and nothing weird would happen. Everything would be fine. You would get a normal answer. But look at some of these other functions. What about the square root of x? Here, the natural mathematical domain for that would be x would be anything greater than or equal to 0. Because if you plug in anything less than 0, in other words, a negative number, you would get an imaginary solution. You wouldn't get a real solution. So the natural mathematical domain for that is x is greater than or equal to 0. Not all real numbers, but all the real numbers greater than or equal to 0. What about 1 over x? There's one number that would make this very strange. If you plug in 0 for x, then you have an undefined number. 1 over 0. Like, you can't divide by 0. It's not allowed. And I can tell you more about that later if you want me to. But you probably already knew you can't have a 0 on the bottom of a fraction, which is another way to say you can't divide by 0. So here, x can be any number except 0. So the natural mathematical domain for a function like that is x is everything but 0. X is all real numbers as long as it does not equal 0. All right, here, this is an interesting one. Here, we don't want x to be negative because that would give us a non-real answer. But we also, if we plug in 0, that would also be bad because the square root of 0 is 0, which would make this whole fraction undivided because we'd be divided by 0. So what can x be? X can be anything other than negative and other than 0. So that means x is everything greater than 0. Okay, so look at this example, and for each of those following graphs, state the domain and range. You may want to pause this to see if you can do this by yourself before we do it together. All right, I'm noticing that it has an arrow. Right here. It only has a point right here, not an arrow, so it doesn't continue down and to the right forever, but it does continue up and to the left forever. So my domain then would be everything from negative infinity on the x-axis all the way to 8 on the x-axis. So I could say negative infinity, comma 8 with a bracket on the 8, or I could just say x is everything less than or equal to 8, which is what they say here. What about my range? What's the lowest value on this y-axis that is included in this curve? It would be this value right here, which is what? Well, because it gives us this ordered pair, this would be negative 2. So the lowest value this gets to on the y-axis is negative 2. What about the highest value? It goes up forever, so infinity. So I could say negative 2, comma infinity with a bracket on the negative 2. Or you could just say y is everything above and including negative 2. Or y is greater than or equal to negative 2. What about part B here? This thing continues on forever up and to the left and forever up and to the right. So my domain, since it is forever left and forever right and it includes everything between it, would be all real numbers. I could say negative infinity to infinity, or I could say all real numbers. The range, however, this thing does have a lowest point. It doesn't continue down forever. So what is this lowest point? Look at this ordered pair. It tells us that the lowest point right here is negative 1. So it would go from negative 1, and it goes up forever. So negative 1 to infinity would be my range, or I could say y is greater than or equal to negative 1. Here I am not given a graph. Instead, I'm given a function, like an algebraic definition or rule as an equation for this function. All right, so for part A, f of x equals the square root of x minus 5. So what values of x would be good? What values of x would be bad for this? What don't we want to happen inside of that square root? We don't want it to be a negative number. So then I would say I don't want x minus 5 to be less than 0. Or I could say, I'm going to say it a different way. I want x minus 5 to be greater than or equal to 0. And I could solve that little inequality by just getting x by itself. I would add 5 to both sides. And I would get x is greater than or equal to 5. And that is my domain. So for this function, x is good as everything greater than or equal to 5. All real numbers greater than or equal to 5 are good for the domain of this function. Part B, think about what's something weird that can happen with a fraction to make an undefined answer. 0 on the bottom, right? So we would say we would say the domain is x minus 5 is everything but 0. So x minus 5 is not equal to 0. That would be the domain. I would just solve for x by adding 5 to both sides. And I would get x is not equal to 5. So so this is the domain. That means x is all numbers, all real numbers except for 5. You put any real number you want to in for x and get a nice answer, except for 5. If you put 5 in, you have an undefined answer. So that's not part of the domain. All right, and then here, a couple of strange things could happen with this problem. One, we could get a negative number under this radical. So x minus 5, let's say I'm running out of room here. We say x minus 5 must then be greater than 0, because if we get a number greater than or equal to 0, if we get a number less than 0, we would be imaginary. But also, we don't want x to be we also don't want x minus 5 to be 0, because the square root of 0 is 0, and you have a 0 on the bottom of the fraction. So not only must x minus 5 be greater than or equal to 0, it must be strictly greater than 0. No equal to sign. Because if it's 0, it's x minus 5 is 0, you still have a bad situation. All right, so again, we add 5 to both sides, and we get that our domain is x is greater than 5. That's our domain for that problem. And if you graph that, you would see that as well. Let's see here. So for that last problem, if you were to graph it, you would see a graph like this. And we can see that there's a vertical asymptote at 5, which means it doesn't equal 5, but it's everything past 5. So everything from 5 to infinity. Or you can say x is greater than 5. I haven't talked about the range yet. So the range for this function, you want to say what all values could possibly come out of this function for the values that you plug into it. Whatever you plug in, the square root of any number is never going to be negative. Right? So, like the square root of 4 is 2, the square root of 25 is 5, the square root of 0 is 0. You're never going to get a negative answer when you take the square root of something. You could get 0, but you won't get anything negative. So the range then is what values you get. The range then would be everything greater than or equal to 0. Why is everything greater than or equal to 0? If you graph this on your calculator, you could also just kind of look at it and tell what the range is. That the range on the y-axis is everything from 0 on up. Like all these values, all these infinitesimally small values are included somewhere in this curve. But if you go down below 0, that's not the case. All right, same thing here. What all values could you get for when you plug something in for x? All right, if I plug in a really big number for x, then I'm going to get a really small number because I'm going to have a big number on the bottom. 1 divided by a really big number is a really small number. But there is no number I could put in where I would get 0. And if I put in a really big negative number, I get just a really small negative number. But again, I can't put in a negative number that would ever give me 0. So the range is everything but 0. You can get any number as an answer, but you will never get 0. If you graph it, you can tell by looking at the horizontal asymptote that all these values on the y-axis are good, except for this horizontal asymptote of 0 here. All right, now one more situation that we need to talk about with domain is sometimes there's a mathematical domain that, like the natural mathematical domain, does not apply to a real world situation for that function. Let me give you an example of that. Let's say you had the area of a circle. Apologize for how terribly sloppy that is. But what is the area of a circle? A equals pi r squared. Or you might say the area as a function of r equals pi r squared. Either way. So this is using function notation. All right. So R would be the independent variable. It would be like X, and A would be like Y. So what are the values that are possible for R? Well, mathematically, R could be anything, any real number, because you can put in any real number and square it and get another real number. But because this is dealing with the area of a circle, what makes sense in real life for a circle, for the radius of a circle? The radius could not be negative, because you're measuring a radius, you would never measure it as a negative distance. Also, the radius couldn't be 0, because if the radius was 0, you wouldn't have yourself a circle, you'd have yourself a point. So we would say R would be greater than 0 for that domain, for a real life situation. Even though mathematically, the natural domain for R is all real numbers, because it has to do with something, an application here, the domain is limited to R being greater than 0. What about the range? What about A? What can A be? What can the area of a circle be? The area of a circle can't be negative, it can't be 0. The area of a circle must always be something, any positive number. So the area of a circle is anything greater than 0 also. So that would be the range. All right, so look at number 1 right here for the same reason. We're a real life situation. A driver who exceeds the speed limit receives demerit points as shown in the table. So if you are 0 to 10 miles per hour, or sorry, this is international, kilometers per hour. Over this, if you're 0 to 10 kilometers per hour over the speed limit, you get 2 demerit points, not including the 10, but you get 2 demerit points. If you're between 10 and 20, including the 10 but not the 20, you get 3 demerit points. If you're 20 to 30, you get 5, 30 to 45, 7, anything more than 45, you get 9 demerit points. So what is the domain? The domain is all of the X values included in this situation. So everything greater than 0, not 0 itself, because if you're 0 kilometers per hour over the speed limit, then you're going the speed limit. There's no reason to get demerited for that. So anything greater than 0, it includes everything between 0 and 10, and this is everything between 10 and 20, everything between 20 and 30. So nothing is skipped, and it goes all the way past 45. How far past 45? Greater than 45 means everything to infinity. So the domain then would be from 0 to infinity, or you could say X is greater than 0 would be another way to say that. The range are all these demerit point values. So the only possibilities would be 2, 3, 5, 7, and 9. So the range is only those numbers. The range is, we would just say 2, 3, and the rest of them. All right, I'm not going to write them because it's so hard to write, but you can see I'm going to say 2, 3, 5, 7, and 9. That's what the range is. All right, here on the second one, this graph shows the temperature in Barcelona over a 30-minute period as the wind shifts. Explain why a temperature graph like this must be a function, because you'll never be 2 temperatures at the same time, right? A function has to have one output for an input. So let's just say at 5 minutes past when we started recording, you're not going to record 2 different temperatures in that same moment. You're going to record 1 temperature. That's why it's always going to be a function. Find the domain and range. Well, just look at the graph. So where do we start on the x-axis, or we could say on the t-axis? We start at 0 and we stop at 30, and everything in between is covered somewhere in that curve. So the domain then is 0 to 30. You could do it. You could do it like with that kind of thing. Or you could do it with the brackets. I'm good either way. 0 to 30. Like that. That's the domain. And the range, we would want to say, well, how low does it go? 15 is the lowest it goes, and it hits everything between, above 15 until you get to 25. Nothing above 25. So everything between 15 and 25. So we would say the range goes from 15 to 25. And it does actually hit. It appears that it actually does hit 25, and all the way it does hit 15. So we include those numbers. All right. And I think that's enough. I think you've got enough information to do some damage on exercise 3C about domain and range. Good luck to you on that, and I will see you next time we have class. And I'll be glad to answer any questions you have at that point.